产业推动力、组织凝聚力、人才支撑力、国际影响力，为加快建设以科技创新为引领、先进制造业为骨干的现代化产业体系，为实现中华民族伟大复兴做出新的更大贡献。
买经纪人上京东。
科技向善，向心而行，助力科技强国建设。建行科技金融正发力。我们善于陪伴，从愿景到实践，倾力支持企业不同阶段差异化金融需求，为每一次跃动的创新灵感注入实现梦想的力量。我们善于融合集各方智慧，发挥集团金融牌照丰富优势，为每一个前行的科技星火点燃照亮理想的火炬。我们善于开拓，培育多元化接力式科技金融服务生态，为每一位探索的时代先锋赋予破浪疾驰的能量。在创新驱动发展的路上，我们以科技为引擎，创新技术流、星光 Star、投资流等各类科技创新评价工具，实现不看砖头看专利，加强科技金融专业化机构建设，从源头对接科技企业，实现金融服务精准触达，健全差别化政策体系，激发服务科技企业内生动力，守护科技梦想，与科技企业并肩同行，迈向科技强国璀璨征程。科技金融，善建未来。
总有一种追求，矢志大国崛起梦想；总有一种力叫电子事业腾飞；总有一种信念，坚守立会围攻初心。1962年，在王征、王子刚、刘寅等我国电子通信事业老前辈的倡议下，中国电子学会正式成立。从第1届电子学术年会到中国云计算大会，我们深耕学术沃土，促进行业繁荣发展。从聂荣臻元帅为电子学报题写刊名，到获得中国出版政府奖，我们紧跟学术前沿，促进中外学术交流蒸蒸日上。从第1届电子科普大会召开，到科普电子周举办，我们点燃有志者的科技梦想，激励青少年人才扬帆起航。从踏上出访的旅程，到成功举办世界计算机大会，我们积极承担国家科技外交职责，发出中国声音，贡献中国智慧。新的时代，我们秉承民主办会、立会为公的初心不改，坚持4个服务，当好桥梁纽带的职责不辍，向世界一流科技社团大步迈进。我们成功举办世界机器人大会等100余场国际盛会。国家主席习近平向2015世界机器人大会致贺信。我们深度参与国际科技治理，连续多年参与联合国互联网治理论坛，与30余家国际机构深度合作，发起成立世界机器人合作组织，携手国际伙伴，构建共赢格局。我们聚焦行业热点，举办了中国电子信息年会等1651场高水平学术会议，173万人次参会，促进学术思想交流互鉴，铺就出勇立潮头的腾飞之路。我们用心建设青年科学家俱乐部、青年女科学家俱乐部，打造电子信息人才能力提升工程，让电子科技工作者汇聚一堂，为加快建设世界重要人才中心和创新高地注入强劲动力。我们坚持公平公正，建立科学评价体系，提名获国家科技奖数量逐年增加。我们打造精品期刊，提高学术科研论文质量，为推动电子信息科技进步乘风破浪，奋勇前进。我们制定500余项团体标准，服务上1000家企业，助力科技创新与产业创新深度融合。我们进入乡村，举办烛光义教公益科普活动，发挥科教优势，举办青少年顶尖赛事，启迪着200余万青少年的科技梦想，助力青少年用万千烛火汇成知识的熠熠星河。我们发布100余项前沿领域智库成果，成立中国数字经济100人会、中国人形机器人100人会等智库平台，构建智力方阵，聚集其强大的智力宝库，为国家科学决策积极建言献策。峥嵘岁月铸心智，砥砺前行攀高峰。当 当前的中国电子学会各项业务蓬勃发展，现拥有个人会员17.8万人，团体会员1900余家，专业分会48个，专家委员会10个，工作委员会9个，31个省、自治区、直辖市、计划单列市有地方电子学会。奋进的时代，中国电子学会也创造了璀璨的成绩。新的征程，中国电子学会将用习近平新时代中国特色社会主义思想凝心铸魂，聚焦4个面向，持续推动5化发展战略，着力提升创新引领力、产业推动力、组织凝聚力、人才支撑力、国际影响力，为加快建设以科技创新为引领、先进制造业为骨干的现代化产业体系，为实现中华民族伟大复兴做出新的更大贡献。
科技向善，向心而行，助力科技强国建设。建行科技金融正发力。我们善于陪伴，从愿景到实践，倾力支持企业不同阶段差异化金融需求，为每一次跃动的创新灵感注入实现梦想的力量。我们善于融合集各方智慧，发挥集团金融牌照丰富优势，为每一个前行的科技星火点燃照亮理想的火炬。我们善于开拓， 培育多元化接力式科技金融服务生态，为每一位探索的时代先锋赋予破浪疾驰的能量。在创新驱动发展的路上，我们以科技为引擎，创新技术流、星光 Star、投资流等各类科技创新评价工具，实现不看砖头看专利，加强科技金融专业化机构建设，从源头对接科技企业，实现金融服务精准触达，健全差别化政策体系，激发服务科技企业内生动力，守护科技梦想，与科技企业并肩同行，迈向科技强国璀璨征程。科技金融，善见未来。
总有一种追求，矢志大国崛起梦想；总有一种力量，聚焦电子事业腾飞；总有一种信念，坚守立会围攻初心。1962年，在王征、王子刚、刘寅等我国电子通信事业老前辈的倡议下，中国电子学会正式成立。从第一届电子学术年会到中国云计算大会，我们深耕学术沃土，促进行业繁荣发展。从聂荣臻元帅为电子学报题写刊名，到获得中国出版政府奖，我们紧跟学术前沿，促进中外学术交流蒸蒸日上。从第一届电子科普大会召开，到科普电子周举办， 我们点燃有志者的科技梦想，激励青少年人才扬帆起航。从踏上出访的旅程，到成功举办世界计算机大会，我们积极承担国家科技外交职责，发出中国声音，贡献中国智慧。新的时代，我们秉承民主办会、例会为公的初心不改，坚持4个服务，当好桥梁纽带的职责不辍，向世界一流科技社团大步迈进。我们成功举办世界机器人大会等100余场国际盛会。国家主席习近平向2015世界机器人大会致贺信。我们深度参与国际科技治理，连续多年参与联合国互联网治理论坛，与30余家国际机构深度合作，发起成立世界机器人合作组织，携手国际伙伴，构建共赢格局。我们聚焦行业热点，举办了中国电子信息年会等1651场高水平学术会议，173万人次参会，促进学术思想交流互鉴，呼救出勇立潮头的腾飞之路。我们用心建设青年科学家俱乐部、青年女科学家俱乐部，打造电子信息人才能力提升工程，让电子科技工作者汇聚一堂，为加快建设世界重要人才中心和创新高地注入强劲动力。我们坚持公平公正，建立科学评价体系，提名获国家科技奖数量逐年增加。我们打造精品期刊，提高学术科研论文质量，为推动电子信息科技进步乘风破浪，奋勇前进。我们制定500余项团体标准，服务上千家企业，助力科技创新与产业创新深度融合。我们进入乡村，举办烛光义教公益科普活动，发挥科教优势，举办青少年顶尖赛事，启迪着200余万青少年的科技梦想，助力青少年用万千烛火汇成知识的熠熠星河。我们发布100余项前沿领域智库成果，成立中国数字经济100人会、中国人形机器人100人会等智库平台，构建智力方阵，聚集其强大的智力宝库，为国家科学决策积极建言献策。峥嵘岁月铸心智，砥砺前行攀高峰。当前的中国电子学会各项业务蓬勃发展，现拥有个人会员17.8万人，团体会员1900余家，专业分会48个，专家委员会10个。 这里，你看到过什么？一个让人惊叹的瞬间，一个最终呈现的成果。但值得被记住的，不仅仅是在这里，还有你没看到过的一次次跌倒，一次次破碎，一次次被推翻。我们曾经失望、沮丧、怀疑，想过放弃，甚至绝望。但是心里总会响起一个声音：
再试一次，偏差只有3毫米了。Try again.
Good job.
再试一次吧。开脆稳定，协同运行。
再试一次，问题就会成为线索。
再试一次吧。再试一次。
Le point d'apport est délagé. On réajuste.
加油，再试一次。
再试一次，再试一次，积累终会爆发力量。
再试一次，继续前进。再试一次，继续突破。
再试一次，未知终会成为方向。每一次尝试都会有相逢，每一次坚持都终有抵达。
再试一次，再试一次，
再试一次，
再试一次，为了生存活活。
每一次都算数。尊敬的
Ladies and gentlemen, distinguished guests, good morning. It's a great pleasure for us to welcome you to the second session of the main forum of the World Robot Conference. The theme of this morning is driving the applications. We need really to focus on the exact and real application scenarios so that we can enable all the industries with robotics. So today we're going to talk about the applications and the application of these technologies.
The applications. The growth of the robotics industry hinges on the powerful impetus of application-driven development, and only by anchoring real-world scenario demands and bridging the last mile for technology implementation can robots step out of laboratories and empower thousands of industries. Today, we will exchange views on driving applications and explore practical pathways for technology development and industrial advancement. 接下来呢，让我们有请中国电子学会理事会党委书记、中国人形机器人与具身智能百人会理事长张峰先生发布2026人形机器人产业发展报告。Please welcome Mr. Zhang Feng, President of the China Humanoid Robotics and Embodied Intelligence Committee of 100, to release the 2026 Humanoid Robot Industry Development Report.
各位嘉宾，各位朋友。
Ladies and gentlemen, dear friends, good morning. It's a great pleasure for me to be here to present the Humanoid Robotics Industry Development Report compiled by the China Humanoid Robotics and Embodied Intelligence Committee of 1000. We know that humanoid robots are robots that resemble the humans in both appearances and behavior and possess some of all human-like characteristics, including hat, torso, limbs, human-like movements, facial expression, language capacities, and intelligence. As a product of the deep integration of AI and robotics, humanoid robots are widely regarded as the optimal embodiment of embodied intelligence. They are evolving from moving on stage and running on the track to being used in homes and working in factories, and are poised to become the next disruptive product following computers, smartphones, and new energy vehicles. And they are expected to play an important role in manufacturing, warehousing, and logistics, emergency response, household services, medical rehabilitation, and other scenarios. We believe that they will profoundly transform the way human lives and work. Humanoid Robotics Industry Development Report 2026, hereafter referred to as the report provides an in-depth analysis and assessment across 5 dimensions: industry overview, development trends, technology landscape, industry value chain, and application scenarios. It mainly covers the definition, scope, and key concepts of humanoid robotics, its strategic significance and future outlook, with this particular focus on the developments in 5 countries: China, the US, Germany, the Republic of Korea, and Japan. The report systematically reviews the core technology system of humanoid robotics, provides a comprehensive overview of the entire industry chain of the robotics, and offers an in-depth analysis of 7 major application scenarios. We present 4 key findings in the report. 1, technology innovation has entered a new phase of emergence of innovation clusters. Technological iteration is speeding up, and complete robot products are rapidly becoming more sophisticated and intelligent. Humanoid robots are continuously gaining stronger capacities in environmental perception, planning and decision-making, and motion control, with steadily enhanced adaptability and stability in complex environment. Secondly, the industry chain has achieved a dual leap both in quality and efficiency as well as overall capacity. China has developed end-to-end manufacturing capacities across the humanoid value chain, covering everything from key chips and components to complete robots. Thirdly, industry applications have entered the deep water phase of full-scale rollout, rapid moving from small-scale trials towards routine deployment and large-scale adaptation. And in the first half of 2026, the humanoid robot shipments in China exceeded 40,000 units, further increasing China's share of global shipment to 97%. Fourthly, ecosystem development has fostered a new paradigm of coexistence and co-prosperity. A four-pronged industry ecosystem, that is to say, an industry's ecosystem with 4 pillars, is standing up to take shape, driven by standard development, underpinned by talent development, expanded through international cooperation, and supported by innovation infrastructure. Going forward, the China Humanoid Robotics and Embodied Intelligence Committee of 100 will continue to serve a bridge, link, and think tank within the industry, contributing to the development of the humanoid robotics industry. Thank you very much. Thank you, President, for your very innovative and inspiring introduction. Now we give the floor to Mr. Wang Xingxing, founder and chairman of Unitree Robotics. His topic is from exhibits to products, the next decade of the humanoid robot industry. Ladies and gentlemen, distinguished guests, good morning. It's my great honor to talk to you at the WRC. First, I'd like to review the company's history. My company was started in 2016. That was in August, and we are now in August, so about a decade. And in the very beginning, we started to work in robotic dogs, and now we are working in humanoid robots. And you can see that the Unitree G1 is a fair success. It has become a world benchmark. So most of these products provided by Unitree, or in that way, you really being used in the world, are very similar looking to the Unitree G1. And in this morning, we have some scenarios, like we have the robot dance at the Chinese the Spring Festival Gala. That is a warrior robot show. So we have been combining the Chinese culture, these movements in Chinese Kung Fu, to be compiled and trained by AI, and it can be presented on the stage. The most advanced humanoid robot technology and Kung Fu culture of China are integrated into one, and actually the overseas audiences are really welcoming this kind of performance and showcasing of our technology. And also in February, we also had an event at the China's sacrifice hall to the heaven, and over 100 robots. So you know that this sacrifice hall has over hundreds of years of history, and this is like linking the past and the current technology. So the sense of time traveling is really astonishing. And currently, really interestingly, we've been promoting how these robots can be applied in real-life scenarios. That, like 2 decades ago, we started to develop industry robots, and we are also using these robots to produce robots in our production lines. And in most of these cases, we are actually having them to work for the other robot. And actually, we are asking them to have these movements so that they can help these other robots to be produced, to be born. And actually, they are not as efficient as human hands. When we have new tasks, we need to train them from the scratch. So we want them to have a much improved general capacity. I think this is the bottleneck that we are having universally in the world. And you can see that we have the robots run, and their speed exceeded 10 meters per second. So please enjoy this video. It's already a treat for all of us.
The first generation based on the first generation 2023, and this is the first product of our Humanoid, very classic. Also, we add wheels on it. It's more fragile, and it's more agile and dexterous. In addition, we know currently robots are driven by AI. AI is driven by data. How many data, especially high-quality ones, we have how much AI. So we collect ourselves or collaborate with local companies to collaborate and provide for others and for ourselves. This is very important. And currently, I feel that real AI training data is based on a huge amount of internet and real ones, and collect some real ones. I think this is very necessary. Based on amount, the real human data is more important. And we need real world data. We need to align robots with physical world. Including this May, we released the first one. Bulk release 3 meters high, about 500 kilograms when loaded. You'll be interested in how it's applied. This is like a off-road vehicle. It's not for family or city use. It's for outdoor and working in a complex environment. shipment. And it can transform into quadruped, so it's more stable. This is why we say we need to pick it up to really do pre-sale of this, because for quadruped it's more stable and good at traverse barriers, so it's like off-road vehicle. And we have some demos here. Multimodal P2B auto AI motion generation. Like some classic motions is pre-trained, but for this part the motions are generated in real time, and because of the semantic, so there's some latency for each sentence. There is recognition and upload to the cloud and generate motions and verify it. When it's approved, no problem, and then download to the robot. So several seconds of latency, but we hope in the future for real application, it's real-time generated, not pre-trained. Because of this, there's a time needed for language processing, so there's a latency. This auto generation has a downside. Each time there is a difference for the motions. Each time for the same sentence, the motions may be generated differently each time. Also, like the robots in real meeting room doing some work, I think it's important. Like our generations, our company sometimes is messy, so to sort out the meeting room is necessary. So it's troublesome. Companies have office rooms, so it's the collection training. We make the meeting room messy and have this robot to restore it. Because it's a P2P, so currently the motion efficiency is relatively slow. And it's multitasking. We put 7 to 8 different tasks. And for one model to switch from one to one to automatically switch, and it's resistant to interference. Because it's AI real-time generated and percepted, so you can see the motion is not that fluent because for each step you need to infer the next step. So it's not as fluent as pre-trained. And this video, it's not edited. It's a real one shot. And we can focus on that. When there's inference, it can conquer it. Resistant to this. Due to time limits, I will not continue it. We have this full video on our official website. We have developed this function like sorting out the meeting room is useful and not very difficult to achieve. We believe it's meaningful to do this. Also, this is based on the semantic auto generation. Previous one there was no interaction. However, this one the motion can really deliver complete some missions. A multimodal is on board. And resistant to interference is not a rigid motion. Including previously we launched the wheeled robot. It's lightweight 20 kilograms. And the load and endurance is very strong and resistant is waterproof. Can be used outdoor. It's lightweight, so it's good for industrial and daily scenario. Very convenient. And we moved some humanoid robots technology into it to make it more autonomous. Very strong loading capacity. We hope that it can use for hiking. And this model will make it more agile. It's very cost efficient. In JD, Taobao, we have retail or pre-sale. Please pay attention to it. And we have been developing this for only 3 months, so this is not an official launch. It's just a preview. 12.6 meters per second, surpassing the quickest human, including the height. Almost the human record is broken. And 2026, and our company was on the list of Times magazine. And also a review of recent years' milestone for AI model. Mainstream is survey and world model. This year we hear a lot of the world model. Our company for AI model, we have been investing a lot. And currently it's where we put the most resource, finance and human capital since 2022. We were focusing on the world model, but by the end of 2022, the result was not satisfactory, so we changed the direction. And in recent years, we have been allocating more resources on that. This is exciting. When real generative robots can be applied in our daily life, most importantly, the bottleneck is the generalization. That's the limit. Any generative AIs in a fixed scenario with enough collection, this success rate is almost 100%. However, if the objects or environment is changed, then the success rate can be declined dramatically. We hope in the future, 2 to 3 years or even 10 years, one day we can really see a robot can be introduced into a strange scenario and it can achieve 80% of task success rate. I think that's the ChatGPT moment. I believe that's an explosive point, and the assessment criteria is simple. You brought a robot to 80% strange scenario, and with the semantic orders, it can achieve 80% of task. I believe this is a tipping point. How come now to achieve this? The biggest bottleneck is currently AI models input-output. It cannot be aligned with real robots. Now the real robot model to give it order to move or to assemble some things or to move objects, the entire process is okay. Roughly it can achieve that. However, for the final centimeters or millimeters, there is disalignment. It cannot really align with the real world like the tensor and the deviations and at the final details, and this is a very severe limits and challenge bottleneck for our humanoid robots. The data and the real world disalignment. The reason is in body model and for symmetric language model. It's full digitally programmed. It's precisely limited in data space. There's no much disalignment, and there's little loss in the precision. However, for robots, for each time of the input and output, there is a loss of precision, and that resulted in the generative results in the world. Now it's not to our satisfaction, and I'm sure in years we will resolve this problem. Also introduce, yesterday we mentioned this, our company's preview. In past years, we have done a lot of programming for AI development. However, for AI's real application for robot development, we are lagging behind. So recently we have been pushing forward with this. Physical AI use the most cutting edge AI big model, and we set some laws and orders and some limits, and it can search essays online, the research results and open source results online, and so it can make its own coding and programming and ensure in a safe limits it can program and operate and can retrieve some big models and do some recordings and some assessment. The AI model can achieve by itself, or humans can participate because human experience counts. It's easy for us to make a judgment. So once it's in operation, the development efficiency for robot will be accelerated and iteration will be quicker. After a while, it can run this autonomous programming, then it can achieve a lot. This is a coding agent. It do some of its own coding and programming. You can try it. Now, mainly simple, even augmented learnings and codiness and programs. The results is quite satisfactory. And if we put it in the simulated scenario for training, once it's done, we move it to the robot and do the AI model, and with humans to rate it, to verify the result, and then feedback to the programmed agent. So this is a positive loop. This is the simplest example. In real practice, this can be more complex, I believe, with this. This is meaningful for our next few years of endeavor. The purpose for this, some simple reasons. First, with each month, each year's enhancement of the basic model, it can reach the result. So it's a positive loop, and it can push forward with the global development and can use multi-source data. For human, the efficiency is limited, but with this autonomous looping, we can do including real-world and humans data, so efficiency can be raised. And with more multi-tiered allocations and deployment, and we can use more assessment indexes, we can ensure the quality, so we can scale it up, and each month we can add more skills.
So it's it's not like this day or this month I've produced something and then I just throw it away. No. So the evolution efficiency of the robots will be improved largely. That's what we need to do in the future, and that can also open up or say usher in a new chapter of self-promoted evolution for physical AI and robots. In the past decade, our company started to be part of the World Robot Conference in 2017 and 2018, and we received great inspiration. And in the next decade, because people will be focusing more and more on the AI, the robots will be evolving much more rapidly in the future. So I think this is a new start. And in the interest of time, I'm not going to elaborate. Thank you very much for your attention.
下面让我们有请德国国家工程院院士
The moderator will repeat himself later.
沉默的超级市场，当机器人成为家庭新成员。Please welcome Mr. Wolfgang Burgard, member, German National Academy of Science and Engineering, and professor, University of Technology, Nuremberg.
Wonderful, thank you. Good morning, and it's my great pleasure to give this presentation here today in front of this fantastic audience and after this fantastic speaker before. I was asked to talk a little bit about how to get actually humans into our everyday life, and with this title, The Silent Supermarket, when robots become the new members of the family, it's basically addressing the challenge of building robots that are supposed to enter our everyday life and perform their task among us and in our families and at our homes. And I want to talk a little bit about what that actually entails from my perspective. And in the end, that bringing robots into homes basically means that we need to go beyond that what we have done thus far, namely looking at one of the other big use cases of robots and embodied robots, which are basically industrial or new industrial settings or basically manufacturing. Right, so the most promising application domains for that what we call embodied robots or embodied AI currently are manufacturing, logistics, and home assistance. And home assistance is obviously one of the most challenging tasks, which I will explain in a few seconds. But what we need for this is basically robots, and currently we are talking about humanoids as the most promising platform for these purposes. Plus, and this is often underestimated, really advanced dexterous hands with additional perception capabilities. I will talk about this in a few seconds. And in fact, computing infrastructure. This is something that we saw sketched also in the previous talk. The ability of robots to perform complex household chores basically means that they need to be able to understand the world. And what that actually means is something that I will explain in a few seconds. Right, and if you want to enable robots to perform complex tasks, then the first task that we need to do is we need to improve the perception capabilities. We have seen in the previous talk like super advanced hardware improvements. I think we have never seen such a development like in the past couple of years when it comes to the advancement of hardware, and we need to go the very same step in the development of the AI and reasoning and perception capabilities of these robots as well, which basically means that we need to have that what is called a world model, or like a model that basically allows the robot to understand the world and predict what is going to happen based on its actions. And this unfortunately goes beyond that what we are right now seeing mostly also in internet scale data systems, basically like systems like ChatGPT and so on, which are mostly relying on vision and language and text. Right? And we have used all the internet mostly in order to generate the corresponding models, but what we actually would need in order to build like similar scale performing robots is more than just text and vision. What we namely also need is the capability to reason about tactile and the sensation of touch, as well as forces. The robot actually need to understand which forces to apply to manipulate the world in a proper fashion. And this is why we are talking about these multimodal foundation models or world models for robot that basically entail this multimodality. And once we have this, we can actually, or we hope that we will be able to generate these complex tasks that the robots need or supposed to do in our households. The major challenge of this is sketched at the bottom of this graphic, is basically the closed loop feedback and the integration of this. If we really want to build robots that learn from their everyday activities in a relatively fast fashion, then we need to go beyond that what we see right now, where we actually get a new model every couple of months. Right? What we would need for that is the ability to retrain and improve these models on a small time frame, basically overnight. And this is unclear how we can do this right now with all the energy consumption and size of these models that we are seeing. So there's a couple of several development tasks that we need, and I only sketch a few ones over here, and my colleagues, I guess, will talk later on today about several of these challenges as well. Right? It's not only hardware, humanoids, and hands. We need to develop multimodal action or world models. We actually also will need to have an ecosystem for data. We need to come up with a strategy that allows us to collect data from all the robots in the world in order to basically generate that what is called the Internet of Robots. And once we have this, we have the ability, hopefully, or the basis for performing lifelong learning, fine-tuning of existing models, and finally also having the human-robot interaction in place, where we can actually not only talk to robots, but also physically interact with them. And a few sentences about what this actually entails. Right? So, for example, if you look at the instruction, tidy up the kitchen, then this can be a relatively easy task, but it can also be enormously complex. And in order to do this, right, a robot needs to basically have a substantial understanding of the real world, right? So first of all, it needs to understand all the objects, but it also needs to know what a clean kitchen actually means. And this is a substantial problem, right? It's basically that what is behind one of these, or behind these world models that allow the robot to reason about what to do in order to accomplish such a task. And here's one example about what we did in this direction. Right? So for example, telling a robot to open a drawer basically means that it needs to understand what a drawer is and where actually the handle is and how the handle is actually used in order to open the drawer. And this is basically what we need to have the robot to understand in order to perform even such simple tasks. And once we have these simple tasks, we can actually also chain them to generate more complex actions. This is one solution for this problem. The alternative is to use a full multimodal action model that basically does this in an end-to-end fashion. But here's an example of how this can be done. For example, you train the robot on specific individual actions, right, and label them according to the language, and then at the same time you basically, or later on, you can use your favorite foundation model, text model, to basically generate code that executes these actions, right? So this is basically what you can do if you're not doing this in an end-to-end fashion with a complex world model. Right? And if you apply this in practice, and here you can basically see this task that we gave the robot, tidy up and turn on the green light, and you can see actually how the robot is actually able to chain these individual actions, like grasping cubes, opening the drawer, placing them in the drawer, closing the drawer, and finally executing this action of pushing the green button. Right, so this is something that we actually need to have in order to perform such complex tasks. Another thing is robots in the wild at home. And here's one example. You saw this messy kitchen a few seconds ago. And now imagine you are a vacuum cleaner and you're supposed to clean the house. And in fact, there are things that a vacuum cleaner should not suck up or brush up as these tools do. Like, for example, jewelry is something that you do not want to take out of your vacuum cleaner after operation. And this is something that also requires a system to basically have a semantic perception capabilities and to understand what the robot actually should do and what the world is and how the robot should actually interact with the world. Right? And one solution that we implemented in this context is basically using foundation models and distilling these foundation models into smaller, in this case a YOLO V8 model, that basically allows a robot to perform this task on an edge device installed on the platform. So basically send every image to a foundation model and ask the robot what to do, either to suck or to avoid, which basically is a policy, and then we use these examples later on to train or to distill a model out of this that runs on an edge device. And you can see here that the learning results basically are corresponding to that of a full-fledged retraining that we did here, and that the energy consumption, that's basically the green curve over here, is substantially lower than as the full retraining. And also the calls to the foundation model decrease over time, which basically means that this system becomes more and more effective. So it basically is able to learn from everyday operation, that closed loop that you saw before, in order to execute its task. And here are a few examples of this robot in action. You basically see the robot avoiding objects that it shouldn't suck up, and when it goes over things, it's a turtle bot that doesn't have a brush, so it doesn't actually really clean up, which helps with the experiments. Right, so this is one of the examples how foundation models can enable robots to really perform complex tasks and that require a substantial semantic understanding of the environment. Another example is grasping. Right? So in the past, grasping has mostly been done based on geometry and measuring grasp success, but there's more when it comes to grasping, because objects need to be grasped in specific ways typically. And this is one example where we use basically foundation models for identifying how to grasp objects. And this is a system called LAN grasp that basically uses these models to figure out where objects should be grasped in order to manipulate them. Right? And here you can see these, on the right-hand side, you see our LAN grasp system that basically performs this type of semantic grasping, whereas compared to GraspIt, a relatively old, I need to say, but still very reliable system for geometric grasping. Right? And here you can see that these robots, or this robot actually performs substantially way better grasps than with than a system that relies on pure geometry. And in a quantitative evaluation with user studies, we figured out that our approach is basically much closer to that how a human would grasp these objects than standard geometry or purely geometry-based approaches. You can even go beyond and go to more complex scenarios where, for example, when the cup has no handle, then the system infers that you need to grasp the cup at the body, right? Or when it is dirty, then it even reports that it shouldn't grasp it at all because that might harm the robot. So this is something that we actually need to incorporate in our future robot, and that's what it actually means when we talk about in generating embodied AI. The same can be done with placing. So here's an example about using a foundation model for properly placing objects, and you can give this robot like an object in an arbitrary orientation, and it basically looks at the object and rotates it in ways so that it is put down in a proper fashion. Right? The last example in this context is bin packing. In particular, when you think about robots helping in supermarkets, then one task could be to basically take all the items from the conveyor belt and put them into your basket or bag. And this immediately raises this question, how to actually do this, right? How do we pack the items into a bag? In fact, in practice, we're using constraints that we don't put heavy objects onto fragile ones, and so on, and there's many more. And the question is, how can we actually get a robot to do this in a way we would actually do this? And this is, again, something where these world models or foundation models might come in very, very handy. So the approach is basically the perception part. We segment all the objects. We perform the segmentation and infer the individual object types and also weights in order to properly manipulate the objects. And then we use a mixed integer programming approach to basically find the box that best suits all the objects and also generates a placement of these objects in the box. And you can see this approach in action here. These are the constraints that we provide to the system. And here is like a relatively simplistic picking strategy. This is all standard. What is added here is a dedicated gripper that we developed for this purpose in order to also handle fragile objects. I will come back to this in a second. So it's basically a gripper that also provides the robot with a sense of touch, which is one of the modalities that we probably will need in the future. Right? And then perform path planning. The interesting aspect here is this question of how to actually understand, how do we actually measure the success of the robot. And for this, we performed a user study. We asked people like, which objects would you put next to another or on top of each other? And from this database, we basically were able to infer that that what we call pecking constraints. And from that, we generate this pecking constraint score that we then can use to evaluate the pecking order provided by the robot. And here are a few examples where the robot basically picks the individual objects and places them in the box in a human-like fashion, so that you can actually see that, or that you would not, for example, put the apple underneath a soda can, for example. And this is something that the system now automatically is able to perform. But that is important in a zero-shot fashion, and this is what what we actually aim at in the future when we talk about embodied robots. Let me skip this. The final part of my presentation is like going to additional modalities. Right? So what we see in particular at computer vision conferences is that they believe that this problem can be solved with computer vision only. And I don't believe into this, because humans develop the sense of touch in order to being able to perform closed loop manipulation, even in the case where they cannot exactly see what they are doing with their hands. And this is something that you also see at the exhibition here, like several companies developing these hands with a sense of touch. And I want to just briefly show you like what I mean by like when I say this is needed in order to create this what we call embodiment, right? Because in the end, these multimodal world models, right, they need to understand how much force to apply and how it actually feels when you touch the world and manipulate the world in order to be successful, and to actually also make predictions about what is going to happen in order to properly plan your actions. Right, and this is what we're using here. We are basically trying to predict the sense of touch, so the perception of the touch sensors given an image of the environment. So we are basically performing image to image conversion, because these are vision-based touch sensors, and they allow us to basically understand and feel the world while we are manipulating it. And this is this is the architecture overview. We are performing here not only real-world experiments, but also in simulation. We trained the system in simulation, and based on this, we are basically now able to perform predictions of the sense of touch. And here you can see the ground truth plus our right now naive version of this prediction system, in order to understand what it would feel like if we grasp